Hi, everyone. We'll start the webinar in just a few seconds. Give people some time to join. I think we can get started. All right. Hi, everyone. Thanks for taking the time to join us today. We'll be starting the webinar in just a few moments. My name is Tina Fabiano, and I'm on the enDAQ Marketing and Engagement team. In a minute, Steve Hanley, our Vice President of Product, will be presenting today's webinar and Q&A session on Get Started with Pandas and NumPy for data analysis. This is the second webinar in our Python for Mechanical Engineers series. If you missed the first one, we'll send out a link to the recording so you can watch it whenever you'd like. During today's webinar, Steve will walk you through how to use Pandas and NumPy data frames to index, filter, plot, and analyze data. In addition to Steve, we also have Becker Al-Qadi, Connor Flanagan, and Sam Ragusa with us today as panelists. They're all on the software team at enDAQ and are incredibly knowledgeable on this subject, so we're excited to have them with us to answer your questions. This is a 45-minute session. As you're watching the webinar, don't hesitate to use the question and answer button labeled as Q&A right at the bottom of the screen. The software team will be able to type some answers to your questions in real time. Then Steve and the team will be able to answer any other questions at the end of the webinar. We'll also have a poll question for you to answer, and at the very end, we'll launch a post-webinar survey. We'd love to have your feedback so we can make sure we're providing you with relevant resources around this topic, and so we can continue to improve our content. We're really excited to be running this webinar today, answering your questions and helping you to get started with Pandas and NumPy for data analysis. So with all that, I'm happy to introduce Steve Hanley, who'll be taking it from here.
Thank you, Tina. Thank you, everyone, for joining. As she mentioned, this is a second webinar in a series that we've been generating and promoting. The first was introducing Python. Now we're getting a little deeper into data analysis. Next, we'll get a little deeper into plotting with the Plotly library. And finally, we'll start doing some webinars using our new library that we've published, the enDAC library for data analysis, specific around our devices, but also a little bit more generic around shock and vibration analysis. So I have a link here to our previous webinar and sign up for future webinars, but you guys are all here, so you know the drill. Before I kind of get into it, I'm going to start one poll question, our only poll question, which is, did you guys come to the last webinar we held a couple weeks ago? And what is your familiarity with Python, if any? Have you started to play around a little bit? You're still brand new. Maybe you've been poking around for a bit and looking for a refresher. The answer to this poll will help guide me as I go through the webinar and know who I'm speaking to. So I'll give you one more moment. Okay, here we go. I can share the results. Pretty good. So a lot of you were not at the last webinar, which is great. You're coming in and you're getting excited for analyzing data in Python. And pretty good range of people that have no experience, up to a few of you are pretty experienced and looking for a refresher. So a good range of folks. Happy to talk with you today. So recap of what we did last week, or 2 weeks ago rather, is we introduced Python and we said, why is it so popular? And it's popular for good reason. It's very easy to use. It's open source. It's very accessible, and it's also very capable. So we talked about that a couple of weeks ago. We also gave a little bit of an overview about how Python requires these different libraries as well as these different environments. And after our webinar a few weeks ago, I had a lot of people come up to us asking they still didn't quite understand Python. So Dave Mannion and our marketing team made this infographic, which I really like, and I'll just quickly walk through. So Python is the engine that does the real execution, but there's all these integrated development environments where you actually write your code and you see the outputs, but it's basically communicating and using Python to do the work. And also there's a lot of libraries. It's an open source, Python's open source. There's all these different libraries that you can utilize, many of which, well, 2 of which we'll talk about today, Pandas and NumPy, the most popular for data science. But there's somewhat like 400,000 libraries that are publicly available. There's many more that are private, of course. But another point I want to make is that there's a distribution called Anaconda, which allows you to package all these things into one download. So I'd encourage you to either do Anaconda or Google Colab, which I'm in now. So I'll send the link out, or Tina, can you send out the link in the chat? I want you to follow along in this notebook. You can save a copy of this notebook to your own Google Drive if you want to stay in the cloud environment, or you can download a IPython notebook version, which you could then open in Jupyter, or you could download a .py file, which you can open in any Python integrated development environment. All right. Before I start getting into NumPy, I just want to remind everyone that that Python in general is remarkably popular. So what that means is there's a lot of resources out there. I encourage people to try to get into it and try to start writing code and hitting some roadblocks, and then just Google your problem. You'll find someone else that's had the same problem and found a solution. That's how I learned, and that's kind of my preference for learning. If you like more formal training, kind of like this webinar we're going through today, I linked to a couple that I'd encourage you to check out. I also, in our last webinar, somebody asked, what's a good textbook that you recommend? And I found one when I was traveling last week by this guy named Jake Vanderplas. It's a really good textbook. I was talking to our software engineers. He's also been a really big promoter or a contributor to the open source libraries over the years. What I found was really impressive is his entire handbook is available as a series of Colab notebooks. So for example, if you want to get into Pandas objects, there's a publicly available notebook published by this man that goes through and goes a little deeper. Well, not a little deeper, goes way deeper than what I'm going to go through today. So here's a links to a few resources out there. We only have 45 minutes today, so I am going to fly, but know that there's a lot of other information available. Python is popular, so use it to your advantage. I also embedded a couple pictures of cheat sheets that are publicly available. They might be a good reference. Okay, with that, let's get into it. So first, I'm going to go through NumPy, and then I'm going to do Pandas, and then I'll do a bit of teasing our enDAQ library at the very end if we have time. One of the reasons I sent out, or I want you guys to look at this notebook, is NumPy, for people that are new to programming, can admittedly be a little intense for indexing and things like that. I'm going to go through it because it's a good foundation, but know that once we get to Pandas, indexing becomes a lot more intuitive. So do feel free to skip ahead and kind of play along as we go. All right, what's NumPy? NumPy at its core, and this is direct quote from the NumPy team, is the ND array object. And this encapsulates n-dimensional arrays of homogeneous data types. So everything in an array is of the same type. And one of the real benefits of Pandas is that, NumPy, is that all the operations are being performed with compiled code. And I'll show you what that kind of means a little bit later on. But basically what this means to you is when you're analyzing data, you want to save your data into arrays, because then that can help you do analysis of those arrays with very fast performance. With most distributions of Python, if not all, it will come installed already because it's so popular. But if you need to install it, it's available via pip. So pip install NumPy. Once installed, you import it, and typically it's imported as NP because you're going to call it so often, so people abbreviate it. All right. So to explain what a NumPy array is, I'll first explain what a list is in Python. So here I've defined a list. So I've said LST equals in brackets 0, 1, 2, 3. And then I've printed LST times 2. And when I came from the MATLAB world, I kind of assumed if I multiply this list by 2, every element will be multiplied by 2. But that's not how lists work in Python. It basically concatenated the list against itself. And that wasn't what I expected. If I wanted to multiply every element by 2 in a Python list, I'd have to loop through every element. And I did that here. And now I see, instead of 0, 1, 2, 3, I see 0, 2, 4, 6. That's kind of confusing. And it's not all that simple to write. So here's some of the benefits of the NumPy array. So to create an array, you just can pass in np.array, and then the parameter would be this list you've made. And so here I've printed the array, which is 0, 1, 2, 3. And then I've also printed array times 2 and array plus 2 to show you that those are, for one, easy to write and understand, and it does an element by element operation. Another manual example of creating an array in NumPy would be to create a matrix. So I've created an identity matrix, a 3x3 matrix here, and I've specified the type as a float, a 32-bit float. Remember what I explained what NumPy is. Every element in a NumPy array is of the same type. If you ever try to change the type, it's actually going to copy the array and make a new one. So this is helpful if you're trying to manage your memory allocation and things like that. The software team thought it was important to include. So thank you, Sam. Okay. Now, again, NumPy is not all that exciting, at least for someone that likes seeing pretty data. But bear with me, I'm going to get to pandas in a moment. But I want to show some functions about how you can create arrays without having to explicitly define every element. So there's something np.zeros. So if I pass np.zeros and the parameter 5, I'll have an array length 5. Every element is 0. You do the same with a 2x3 matrix. You can create an identity matrix. I linked here to a bunch of different routines and functions in NumPy for creating arrays and matrices. But typically, you'll probably be creating sequences. Elements are sequentially spaced. So here are a few examples. There's the aRange method, where I can simply just pass in the length. So when I pass in 10, I get an array of length 10, starting at 0 and spaced one integer at a time. I can also, there's parameters I can add to this function call. So I could explicitly say np.arrange and start at 0, end at 10. What I want to highlight, and something that is a little unintuitive, is that when you use this function, the end is exclusive. It's not actually going to be included in the output array. You can also pass in a step size, as I'm doing here. There's another function there for linear space. So this is a little bit more intuitive to use, I think. I typically use this one, where I can define a start point and an end point, so 0 to 10, and I want 6 elements. And so 10 is actually going to be included in my array. There'll be 6 elements, all linearly spaced. There's a similar function for logarithmically spaced, which you can see is the equivalent of basically raising 10 to a linear spaced array. So you kind of have to do a bit of mental math to realize where your starting point and end point in the log space method is. There's also geometric spaced. There's random numbers in NumPy. I'm kind of glossing over this because you'll see in a bit what you can do. But again, try to play around and understand how you create arrays. Once you get into it, you start to see it's pretty straightforward. Here's where it loses me a little bit, which is indexing an array. So here I've created an array from 1 to 10, each one integer space at a time. If I want to index the first item, I need to actually pass in an index of 0. It's 0-based indexing in Python. So that can be a little unintuitive, but that's the way it is. I think it's that way. Software guys can give a better explanation than I, but it helps with memory allocation or something to that effect. I don't know. Again, Pandas makes this easier in a moment. You can also index the last item by just doing a -1. You can do -2 to get the second to last item. You can do some fun things where if you do ::, and then you can define the step size. So I want to get every second item. I could start actually adding a starting point. So do 1, then : 2. So I'll start at an index of 1, which is the second value, and then I'll take every second item after that. You can explicitly define the starting point to the end point exclusive and the step size, which I've done here. So starting an index of 1, the second element, 2, 6 to the 6th index. So it's and stepping of 2. You reverse the order. You do Boolean operations. So you say I want all the values less than 5. You get the idea. You can also explicitly pass in a list to get that defines the indexes. And so I've said I want indexes of 1, 3, and 5, and I get those values here. Here I'm showing indexing of a 2-dimensional matrix. So if I want the second column, I do : 1, again, 0-based indexing, and you can kind of combine that. Again, index is going to be way easier once we get to pandas. That's why I'm rushing through this a little bit. Operations in NumPy are really easy. They're element by element. So once I have an array and I want to add 100 to it, for example, I just can type that one line out, array plus 100, and every element will be 100 plus what the original value was, or multiply it by 2, again, element by element. Here I'm showing in Python, if you want to do something to raise to the power of another value, it's a double multiplication. You don't use the caret. I don't even know what the caret does. It does something, but it doesn't do what I expect. So if I basically square every term to array, multiple times 2, so that's squared basically. Once you have arrays of the same size, you can do element by element operations. So here, if I made another array starting at 0, 5, 10, now I add array 1 to array 2. Remember, my first array is just 1, 2, 3, 4, 5, 6, 7, etc. So if I add array 1 to array 2, it's 0 plus 1, and then it's 5 plus 2, 10 plus 3, and you get the output. Pandas also has nice functions for doing some simple analysis. You can get the size and shape of an array. You get the maximum value, the minimum value, standard deviation, a cumulative sum. So here's some examples there. Cumulative product. There's some constants in NumPy. So there's pi, there's natural E, there's infinity. Some built-in functions in NumPy. Again, I'm glossing through it because this will be a good resource, and I want to get to some of the other stuff while we have time. But there's functions, there's sine, cosine, there's arcsine, etc. in NumPy. And again, you can search for a list of all those functions. Most of them are pretty easy to kind of remember because they're well named. There's rounding. So here I've made an array of 0, 0.3333, 0.6666 repeating. And if I say np.round and then pass in my array and say I want 2 decimal points, here's my output. All right. Now, I got through some of the foundation stuff that's not that exciting. Now I can get into some demos and plots and cool stuff. So here I want to demonstrate why NumPy is as effective as it is. And it's, again, it's using all this machine code under the hood for you. So to demonstrate, I'm going to create a sine wave. So first, I've created a time series. So I've said time equals that linear spaced array with the start time of 0 and end time of the number of steps I want times this the step size, which is 1 over the sampling frequency I want, and then the number of data points in my array, which would be 1 plus the number of steps in the array. And now here I've created a function, which I can explain real quick. To create a function in NumPy, Python, it's def, so you define, and then the name of the function here, and then the parameters. So time, amplitude, and frequency are required parameters. And then this is a keyword argument. So phase equals 0 means I don't have to specify the phase. If I don't, it's going to default to a value of 0. But if I use a loop, I have to explicitly, I first create an output array of the same length of the array time. And then for every element in time, I calculate what that value should be for my wave array. And if I time this, it takes around 2.5 milliseconds to execute, and it's a looping. Now, if I make a function using NumPy's built-in np.sine, so it's using vectorization, I can time it again, and you'll see here it's now 27 microseconds. So it's about 100 times faster than looping. One other thing I did here that I want to highlight is I used a doc string. So, and this is recommended best practice. I'm only starting to do that as I've worked with the software guys a little bit now and seeing the value of it. The guy who kind of started Python or did start Python, I think his quote is, "You read code more often than you write it." So it's good to do good documentation here. So the best practice is that first line of your function is to just do 3 quotations and then a sentence saying what your function does, and then close it here. And now when you do help and put in your function name, you'll get this printed out. And actually, while you're writing code, you see here, it should, if I were to write start writing this function. I think I get some help strings. Well, I won't do it right now because it's a demo, but you'll see it as you're writing code. You get some doc strings that are helping see what that does. So again, 100 times faster to use a vectorization. Why does the vectorization work? Again, because it's using machine code. And to demonstrate this, I use this package called NumPy. I'm not going to get into this right now, but I just thought it was a good example, which NumPy now can convert my original example, which was a for loop, into machine code. And now I'll compare the time. Once I did that, it was execution time around the same as when I used NumPy natively. So I created a data frame. I'm going to show you guys this in a minute. And now I plotted the difference. If I just did a basic loop with and without NumPy compared to using NumPy, basically once you go into machine code, you get that massive speed savings. Okay, that was NumPy, and I went through that quick, but now we get to pandas, which I think are more fun. And then we're going to end again with a bit of a teaser and intro of our enDAQ library for a little bit of data analysis on vibration and shock data. So pandas is built on top of NumPy. And to quote that guy, Jake Vanderplas, I think this is a really good quote. At a basic level, pandas objects can be thought of as enhanced versions of NumPy arrays, in which the rows and columns are identified with labels instead of simple integer indices. Remember when I was trying to get that first item in my list, I passed in that index of 0 and kind of getting a range. It wasn't intuitive to me. It might be to some of the software guys, but Pandas kind of solves this, and you have labels now, which make things a hell of a lot easier. Pandas is, again, uses NumPy under the hood, but it's actually become more popular if you measure basic questions and downloads and things like that. So you should have it included in your, when you've downloaded Anaconda or another distribution, but if not, it's a simple install. And then people typically import pandas as PD because you're going to call it so often. In pandas, there are 3 types of objects. There are series, which are one-dimensional, and then there are data frames, which they're basically a series of series, which I'll show in a moment. And then there are panels, which are 3-dimensional. I've actually never tried out a panel. I've been meaning to get into it. I'm not going to go into panels here today. You get all you really need with series and data frames for mechanical engineering-based data analysis. All right, let's get into it. So remember those arrays I had. So I had an array of time, an array of the amplitude when I made that sine wave. And so I just printed it again to remind us here. If I were to create a series, I could say PD pandas.series and pass in that array. And here's the output. So this isn't all that much different than the NumPy array, but the only benefit is I can explicitly see, oh, this is an index of 1 and here's the value, and here's an index of 4 and here's the value. You kind of see it a little better. But really the value with pandas comes when you add in an index. So now I'm saying, here's my data, but here's the index. And I'm going to say the time is the index. And so now I see a time of 0.004. Here is my amplitude of my sine wave. And they're labeled and they correspond to one another. And where it really comes to shine is I can index now based upon and slice my series based upon that index. So if I want all the values when the time is between 0 and 0.01 inclusive, I can just simply write that out, series 0 bracketed 0 colon to 0.01, and I have this shortened list or the shortened series that satisfy those indices that I filtered it by with those associated values. Another plus in pandas and series is the ability to plot natively. It's a method of a series object, which I show here, but we'll get into plotting a little bit later on. Reminder here that pandas is built on top of NumPy. So under the hood, it's still saved as a NumPy array, and you can get that again by doing series.values or series.toNumPy. But hopefully you see a little bit of the value now when you can use those labels. That's really what pandas is giving us, labels of our arrays. Data frames are 2-dimensional. They're basically, again, a list of series. So with series, it's 1-dimensional. All of the elements in that object are going to be of the same type. But in a pandas data frame, we start to have many different types that we can combine together, all with a common index. And the other benefit is you can easily add to a data frame, which I'll show here. So now I'm going to create a data frame with 4 columns. I'm going to use my function creating a sine wave with just 4 different phases: a phase of 0, phase of 90, 180, and 270. So to create the data frame manually, I'm using what's called a dictionary. So I'm saying phase 0 is going to be my label name, and then colon, here's the array, and then my index of time, and here's the result. So you see this nice, pretty intuitive to understand 4-column table, the data frame with the index of time over here. Again, plotting is really easy. Dataframe.plot, it generates this plot. I'm going to get into Plotly, which is a newer library, and I'll show you that in a minute. And to do so, I'm going to show another example in the data frame is that you can add to it really easily, which I'm doing here. So I'm saying data frame max. This doesn't exist originally. So by saying here's a new part of the data frame and here's the values of it. So data frame with the label max equals the max values in the existing data frame per row. So when I say axis equals 1, that's per row. And then I'm going to create another column for the minimum values. And you see here now, when I print out the data frame, I see these 2 additional columns, and it's tracking the moving maximum and minimum per row. So now with the Plotly library, which we'll be getting into it deeper next week, I can plot this again. And what's really beneficial Plotly is it's all interactive. So I can zoom around right here. I can isolate lines in the legend, and it's still pretty easy to call this. I say Plotly express.line plot. Here's my data frame, and then show it. But again, we're going to get deeper into Plotly in a couple weeks. All right, so far I've been generating data, but most often when we're analyzing data, we're going to be analyzing on data from somewhere else. And so Pandas really helps read data in really nicely. There's one of the first lines of code you're probably going to write is data frame equals pandas.read CSV, and then you pass in the file location of that CSV file. You don't have to use CSVs. It's everyone's kind of default to, but there's a lot of other file formats that Pandas supports. So check that out, but I know everyone likes CSVs, so I'll use CSVs in this example. So I passed 2 parameters in. One is the location of my data frame, which this is publicly available data. You guys could check this out. I wrote about it in a blog a couple months ago on bearing health monitoring. So there's 4 different bearings of different fault conditions. But the other parameter I passed in when I read this data frame was I said the index column equals 0. So what this means is I'm going to, if I open that CSV in Excel, you'll see 5 columns, there'll be time, and then these other 4. When I specify index col equals 1, data frame, when I'm loading it in, it's going to immediately use that first column as my index, and that's what it's done here. Saving a CSV is as easy as instead of read CSV, it's to CSV, and then you specify where it goes. This is true with all the file formats. But now let's get into actually analyzing data. There's a lot of built-in methods in Pandas. So once I've read that in, I can do dataframe.describe, and you see here I get a bunch of metrics per column. So here's my mean value, my standard deviation, my minimum, my 25th percentile. That all comes right out of the gate with that 1 line of code to get a snapshot of what's in that data frame. You can explicitly call for the standard deviation, the maximum value. Remember, it's using NumPy, so doing dataframe.max is the equivalent of saying numpy.max and then giving it the data frame, as you see here. There's quintiles, which I really like. It helps kind of filter away, what's it called, outlier data. You can use, here I'm going to say I want the absolute, the maximum of the absolute values. So I've added a column here to say per row, find the maximum of absolute values. And you can see in this example, here's 0.105, and here's the negative 0.105, but we're getting the absolute value, the maximum of them. And you see that kind of pass through. Nice and easy to do some of the simple analysis. Again, indexing is really easy in Pandas. So here I say I want all the values with a time between 0 and 0.05 seconds. And you see it sliced this data frame that is originally, what was that, 12, was that, yeah, I think that's, I thought this was larger, but okay. It's 120,000 samples, and now I've just got the first 50 milliseconds, and it's the 600 samples, and that's really easy to write and index. You can also use some of the other convention where we kind of went through in NumPy, and that's why we went through that foundation where I say, okay, I want to go from 0 to 0.05 seconds, but I want to take this step. So I'm going to get every 100th data point, and you see how we've stepped, and now there's just 6 values. You can, if you really want to use those integer-based indexing, there's a built-in way to do that. So iLock. So if I want to explicitly say the first 10 values, here it is. Here's a fun thing in Pandas, which is the rolling method. It does really easy window calculations. So something you're frequently going to be doing when you have time series data. So here I've said a window size. So I've said data frame.rolling, and I've passed in a window size. And then you need to then do some type of operation on this window size. So I want the maximum value for every, how much is this? Whatever the shape of the array is divided by 100. So I'll have 100 different window durations. Now when I do this window operation, I still have the same length as before, but I can skip now and say, all right, get me every nth data point. So now I've said I'll actually have explicitly the 100 rows. So every one of these is the moving average, or the moving maximum rather, of the last n, I forget what n is, whatever the length is, it'd be 12,000. Did I do that right? 12,000 data points. And once I have this, it's easy to plot again. Here it is in Plotly, and I see how that moving maximum changed throughout the recording. Okay, now pandas don't have to use, you can use anything as your index. It doesn't have to be time as a float, as a decimal. You can also use date time objects, so it's real calendar time. And I think a good example is to use stock data. This is also a good example of showing why Python, one of the reasons Python is so cool, there's so many different things you can do with it. So there's another library for using Yahoo Finance that they downloaded here. So pip install Yahoo Finance and then import it. And getting the pretty recent results is it's a pretty straightforward call to yahoofinance.download. I passed in a list of the different stock tickers and a start date and an end date. And then I get this data frame returned. And I'm gonna do a little manipulation on this data frame to get the adjusted close, and then divide all the adjusted close prices by the starting time. So I basically see my relative performance. So see here though, my index is an actual date now. It's human readable, which is nice. And if I plot it, I see a plot with real calendar time, and I can zoom and I start getting some more granularity on days, and it goes from 6 months to monthly and various granularity with my grid lines as I zoom around, and it's again a human readable date. That rolling function I showed before, where we passed in a window size of an integer, we can also, once we have date times, pass in a window size using days or seconds or something like that. That's really helpful because a lot of time series data isn't necessarily uniformly sampled. So it's nice that this rolling calculation takes that into account. So we should have invested in Apple a couple years ago. Hopefully some of you did. Now, indexing, once you have date time, is still pretty straightforward, but you need to actually create these objects. So with the date time, we can say, all right, here's a date object of the year 2021, April, the month 4, and the first day of the month. And here's an end date, and now index my data frame based upon these objects of the associated dates. So now I have all the results that were in April. So again, Pandas makes it really easy to index and slice our data frames. Here I'm just showing how you can create a list or indexes of various month end or weekend, or there's a variety of functions in this pandas.date range. Pandas also has a resample function. So here I'm saying resample my data frame with a rule of quarterly. So do it quarterly and get the max per quarter. And now you see that simplified results. All right, I need to fly through this. The last part before I do a little preview on our library is data frames don't have to all be indexed by time. You can have kind of more tabular data with a bunch of different file types and element types. So here I'm downloading data from our cloud. So we have a bunch of recording files. You see the result, and every recording file has these various metrics we're calculating. So you see the serial number, the file name, the size, some of which have simple floats that define the velocity RMS, for example. Then others are full-on lists that describe a resultant power spectral density. So all this can come into the data frame. Again, they're not all the same type as you see, and we can downsample and kind of filter nicely and easily, which I'll do in a second. Now, there was a lot in that that comes out of our cloud, so I'm kind of simplifying and focusing just on a few columns that you see here. I also converted the date time, which was in the number of seconds from 1970 to a human readable date. And then I filtered my data frame. So sort values by the column name. And so now this is the most recent file, the one after that, and it's all filtered. So here I'm just showing that example of not only the downsampling my data frame, but also sorting it very easily. Data frame.sort values, and then you pass in the by parameter and what column name you're going to use. And then ascending equals true or false. Defaults to be true, which I always think is weird. Filtering in a data frame is easy. So here I've created a mask. So I said, I want all the times this column, so data frame.recording TS, so that's my column here, the series, when they're greater than the date time of January 1st, 2021. So now if I filter, and now I'm going to sort by the serial number. So you see here, here's the serial number, but every file had a recording time in 2021. You could also combine filters. So if I use that filter, but also say I only want to see the values when acceleration peak was greater than 100. And now I'm going to sort by acceleration peak. There you go. Where's acceleration peak? So there it's sorted by that one, and I have only the values that passed those masks that I added to it. Again, I'll use the Plotly library, which I'm going to dive deeper into next week, next week, where I can create a bubble chart really easily. I pass in the data frame and I say I want the x-axis to be this column of the data frame, the y-axis to be this column. I want the size of my bubbles to be defined by this column, the recording length. I want the color of my bubbles to be defined by another parameter, the serial number, and I want to see the file name when I hover. So as you see me, this is the coffee file that Tina generated. She's making some sweet espresso. The motorcycle car crash. Now you'll notice here that it did a color bar for when I defined the color based upon serial number, and that was because serial number is a number. So if I explicitly add a new column for the device and make it a string, as type string, and regenerate that plot above, you see I have explicit series for every different device. So again, I'm using data from our devices, but hopefully you get the sense that you can have data frames defining a bunch of random data, but they're still associated with each other. And it's really easy to visualize them with Plotly and other libraries. It's very easy to filter. It's very easy to index, etc. All right, so I'm going to fly through this before we have questions, but I want to show quickly the enDAQ library that we're going to dive deeper into in a couple of weeks. You can download it, pip install enDAQ, then you import it. You can, here I have a file type, and I create a function to import the data set and output some summary information so I can see when it was calibrated, what the file name or the part number was, firmware revision, serial number of the device, things like that, but then also the real data in my file. And then of course I can get a data frame out. So here I'm getting a data frame. So if you don't have our devices, great. Our library is still going to be useful once you get that data frame of acceleration data, which I have here. And now creating a power spectral density is really easy. It's just one call. You pass in your data frame of acceleration data. You specify a bin width. So I'm saying 1 hertz, and you get a data frame of the power spectral density back. And so now it's very easy to plot that. And now I'm doing it again with another function we have in our library. It's a 2 octaves. So if you want octave spaced power spectral density. You pass in your linear spaced one and what frequency you want to start at, how many bins per octave, and now you have a logarithmically spaced power spectral density. Here's some shock data. I'm loading that from another file type or another test. And I'm plotting the time history around the peak event. And now a lot of you have asked about filtering. So we have a built-in method for doing a filter. All I'm passing in is the unfiltered data, or I actually removed the median first. Then I passed in this data frame. I didn't do any low frequency cutoff for a high pass, but I did a low frequency or a high frequency cutoff for a low pass frequency of 150 hertz. And then I plotted it. And you see here now it's much easier to understand data, shock data. It's the same data of here, it's just applied 150 hertz low pass filter. We can also double integrate, which I saw a lot of people that signed up for this webinar asked for examples. Again, I'm going to dive deeper into this in a couple of weeks, but I just wanted to tease it. Here's in our calc integrate function, you can pass in the data frame, how many integrations you want, and if you want to apply high pass filters between each integration. So I got the result and I plotted it. So here's my velocity that changed during the shock event. If you guys remember from power spectral density, or sorry, from shock response spectrums, the change in velocity should correspond to my peak pseudo velocity. So let's see if that's true. About a 700 inch per second change in velocity. Now there's another function in our library to do a pseudo velocity calculation. So you pass in the time series data, the frequencies you want to calculate for your pseudo velocity calculation, the damping coefficient. Here I'm converting back to inches per second, and then I plot it. And you see here that peak, 630 inches per second. It would come closer to 700 if I did a damping coefficient of 0. Now, I flew through all that. It's 12:42. How many questions do we have?
Get a couple of questions that we can go through. All right. So the first one is, does NumPy include statistical analysis?
Yeah. There's where some of the, so here are some of the built-in functions again, so you can get the min, you can do the standard deviation. I believe there's histograms built into NumPy. There's cleaner ways to define those histograms and things like that in pandas, but yes, there's built-in functions for those statistical analysis. If you Google statistical analysis with NumPy, I'm sure you'll come across many examples going through all the different ways you can use NumPy.
All right, the next question is the bin width equal to the sampling rate when creating a PSD plot?
Okay, I'm going to assume that is about our library. Our library wrapped around the SciPy Welch's method for generating a power spectral density. And in here, they have a parameter called n per seg. So that's the segment length that you want every FFT to be that you then average for the PSD. But we simplified the API a little bit. So here we're specifying, I want my bin width equal to 1 hertz. So inside our function, we're looking at what is the sample rate of this time series acceleration data you applied, and we're defining that n per seg to correspond to a bin width of 1 hertz, or if I did 10 hertz, I can try to quickly make sure I have this live. I can show the example. Here's my data frame. And if I do so here's my bin width of 1 hertz. You'll see here every space this is a 20. The next data point is at 21, 22, 23, 24, 25. And now if I say bin width of 10 and I replot this, you should see a more granular. So I get one at 20, the next data point's at 30, 40, etc. So we kind of handle that under the hood, which I think is helpful. You just, regardless of your sampling rate, we'll figure out what you need to do when you define your bin width based in hertz.
All right, so the next question is, which format is faster for computing, NumPy arrays or Pandas data frames? So the context would be creating a Python microservice server that makes API calls and performs analysis.
Well, maybe Connor, you want to jump in, but or Sam or anyone, but remember,
I got this.
Sam, you can give it a go.
Okay, so Pandas uses NumPy as its underlying, like what actually stores and manipulates the information. One time that it wouldn't be consistent speeds would be when you're using arrays or data frames that are larger than could be fit into RAM, in which case pandas would keep it on disk and NumPy would just not be able to do it, unless you account for that. So usually it will be NumPy just because it's a little bit less overhead, but it would be negligible for most situations.
Yeah, thanks, Sam. Remember, Pandas uses NumPy. So as you said, for most situations, it should be no difference. That guy, Jake Vanderplas, I think really described Pandas well. It's using NumPy, but instead of these integer-based indexes, we're giving nice human readable labels.
So the next question is it possible to find the moving maximum max between narrow or smaller ranges in one spectrum? And what about between time series spectrums?
Yes, I think I might need to chat with you after. If you can if you send us an email to success@enDAQ.com and maybe you type that out a bit more, I can give you a notebook that gives the example. Also, if you provide your example data you want to do it on, I can kind of do it all for you to show you the example. But yeah, there's definitely a way to do that.
And can we eliminate the noise repetition with a specific frequency with filter here?
Not sure I understand that one. What is it? It's remove the noise associated with the filter?
Yes, the repeating noise with specific frequency with the filter.
Oh, yeah. Yeah, so here's my example where I was filtering. So I filter, if you would apply, well, Becker, this is either a low pass or a high pass. Or it's a band pass. We would need to do a band stop. So you could do that with 2 lines of code, right, Becker? You'd say, I wanted my filter data to use, let's say you had some noise at 100 hertz you wanted to get rid of. You'd say, my data frame equals enDAQ.calc.filters. You pass in your time series data and say a low cutoff of, let's say 110 hertz. No, I can't do it. That would be wrong, right, Becker?
Yeah, I think our Butterworth filter specifically implements either a low pass or a high pass or a band pass. I don't think we've implemented a band stop. Yeah. It's kind of not the usual calculation we can do. You can definitely explicitly do a low pass.
We can add it to our list.
Yeah.
I mean, you can with our functions here are, some of them are wrappers around SciPy under the hood. And there's definitely a way to do a band stop. So for one, we could add to our list to actually add a nice clean function in our library, but I could also show you with SciPy how to do that. It's just a little messier. But we'll add that to our list, Becker, of adding in a band stop.
Yeah, I think as a workaround, you could do a low pass, and you put the lower frequency bound in, maybe that's 90 hertz. And you do a high pass with the higher frequency bound, maybe that's 110 hertz. And you can just add those together because those are both linear operations. So that should work out. So if you need to do that as just a workaround for now, that should work.
Oh, that makes sense. So you add the resulting filtered arrays back together.
Yep.
Gotcha. Oh, that makes sense.
All right, so the next question is, would you be able to provide an example of working with really large vibration data sets when it doesn't fit in memory, maybe in a future webinar?
Yes. Yes, that's a good, that would be a future webinar. Connor's done some work on that, and there's definitely things we can do, and we could add some other capabilities to our library to specifically handle that. That's a good idea.
And is the enDAQ Python library currently available? And could you cover batch processing multi-files when covering your library in future webinars?
Yes, the library is available. It's on GitHub and PyPy. Again, we're in the process of publishing the documentations on a subdomain of enDAQ. I think it's going to be on docs.endac.com, but the library is already available. Here it is. Right now we have enDAQ.calc that does all the calculations for vibration shock. It doesn't have to be from our devices. There's enDAQ.cloud and there's enDAQ.ide. So that's interfacing with our data in our devices. But we're going to be adding a library, or what do you call it, a module, enDAQ.batch, to do exactly what you said. So we're kind of in process of that, and that would be hopefully the subject of a future webinar for sure.
Great. And we do have one more question. What steps or filters should I use to get velocity and displacement of acceleration signals?
Well, we tried to do that for you. So this calculation here, it's doing kind of under the hood. It's integrating the data with cum traps, cumulative trapezoids in SciPy. But before every integration, it's doing a high pass filter cutoff if you specify it. It's also applying a 2-key window to force the beginning and end to 0 if you specify it, because that's what we recommend to do. But again, we've kind of handled that under the hood for you. So it's just this one line, and you get a filtered accelerometer results, or acceleration, velocity, and displacement. And then you just do a unit conversion, and now you have your velocity and displacement. But you can look at the source code to see how we do it if you'd like. But it's doing a cumulative trapezoid after applying a filter, and then you apply the 2-key window after or before Becker, maybe both. I don't know. We can look at the code.
Yeah, sorry, I would have to take a look at it. I don't remember off the top of my head.
Again, this is all public. You can go and look at the code, and here's the integration. Here's how we did it.
So that was all of our questions.
Great. Well, thank you, everyone. I'll hand it back to Tina. Again, in a couple of weeks or 1 week, we're going to get deeper into Plotly. And then in a few weeks after that, we'll be diving into all these functions in our new library. But remember, it's already available. So do start poking around, and please email us, success@endac.com. I'm really excited to help people. And so if you have examples you want to see, let us know.
Thank you, Steve. All right, so thank you everybody for joining us today. We really hope that you enjoyed the webinar. We really appreciate your questions, and we hope that you found this very helpful and informative, and that you're ready to use the Python libraries, Pandas and NumPy for your data analysis. If you have any other questions or think of something later, don't hesitate to contact us. We'll send out an email in the next few days with a recording of this webinar and links to some helpful resources. Once we close the webinar, a feedback survey will launch. Like I said earlier, we'd love to have your feedback on this webinar so we can improve our content and ensure that we're providing relevant resources that can help you with your analysis. And just a reminder that this webinar is part of our Python for Mechanical Engineers series. Our next webinar will be Python for Mechanical Engineers, Generate Beautiful and Interactive Plots Using Plotly, next week on October 6th at 12 noon Eastern Time. I've included a registration link in the chat, and also it will pop up at the bottom of the survey as well. You can sign up for our webinar notifications too, and we'll contact you with the link to register and inform you of any other upcoming webinars. Again, from all of us at enDAQ, thank you so much for joining us today. We really appreciate your time. Take care. Bye.
Thanks, everyone. Bye.